Okay, we'll continue with this later because I got the okay. All right, so now we're going to present a paper we've written, Ying, Tong, Lai from Geometry Research and myself on the SoK of programmable privacy. So here we are. All right. Is this? Not yet. Okay. So who's going to go to the Fiat Shamir? Raise your hands if you're going to Fiat Shamir. Okay. Okay, that's at least a few. Okay. Michele, we also need to do some work there. All right. Awesome. You ready? Mm-hmm. We're ready. Okay. Let's do this. So we're going to talk today about a work that we've been, is it here? Is it here? Okay. Definitely got a peek right there. So this work on programmable privacy was done in conjunction with Brian Gillespie from InversedTech and Andrew Miller from UIUC. And it was actually funded by the Zcash Foundation, so big thanks to them for enabling this work. We kind of started this work just thinking like, there's a lot of protocols and things out there that claim to do programmability and zero knowledge and privacy, and all of that is a big kind of mess in a way, and we tried to contribute our little grain of salt to make it a little bit less messy. So we need to really start with the programmability stack, right? And what do we mean by private programmability, right? Because this is the context we're getting at. And this is when we're trying to do stuff like smart contracts, but privately, right? And there is several layers and several areas where we need to focus on and look at, right? The first one is the crypto scheme, right? Back in the day, earlier, than 2013 or so, there was no generic scheme to do zero knowledge proofs. You just did the kind of specific computation, and you had a scheme to prove that, right? If it's signatures with short proofs or stuff like that. But today, thanks to amazing researchers that, some of them are in this room, we have actual schemes that you can kind of write circuits for and write, NP language problems, which is great. That's not going to be the focus of our talk. Then you have kind of the next layer, right? When you're thinking about building applications, someone needs to write these circuits, right? And we also have here Dara, who's basically, put a big effort in the past and still today, but to create the first deployed circuit, large circuit in Zcash, right? It definitely is a challenge to write these circuits. You need to think about the primitives and the Merkle trees and the hash functions and how all of it combines, and in a way that it's kind of represented in this constrained system format, right? And depending to what level you allow, a developer to come and write this smart contract, private smart contract, you'll be able to build more applications or less applications, right? If you allow someone to write their own hash functions, well, you'll be able to include more hash functions, right? Albeit potentially not being well tested, et cetera, et cetera. And if you only give access to a higher kind of form of primitive, a more abstracted form of primitive, then maybe less potential applications, right? And then really we have this idea of consensus level protocol, right? And this is also very important. And this is kind of where you come in and put this together, right? If we think about Zcash, for example, as an example, Zcash is kind of a specific purpose protocol at the consensus level, although there's work actually by Kedit to expand that barrier. And if you look at something like Aztec, well, that's definitely kind of the full programmability, right? But at the level of the protocol, you have to define how the flow of the circuits come in and the functions. Usually it's because you want someone to write a program in a language that is well known, right? And then there's kind of a compiler and so on, right? But we're going to focus on that level. And here we have a couple of examples as well, if we think about Penumbra, well, there is kind of like there is definitely the zero knowledge part here, but there is also a homomorphic threshold encryption, right? That is kind of used when you're aggregating different elements, and this is kind of considered part of the cryptographic scheme. At the circuit level, you have batch auctions, right? So like you can program a little bit, you can access a little bit. Actually, you can't really access more of the circuit, but you can program a little bit, right? Like in order to do aggregation and batch decryption, right? And then for example, Renegade, which is kind of like a two-party computation system that allows for private programmability, that's the scheme, the two-party computation. Then you have kind of like the order matching of the application itself for the trades that are happening, and collaborative proving through this computation, this two-party, for the circuit actions. And then like in the consensus level, you have kind of the proof verification and updated of the balances, right? At the consensus level, the update of the state is when that's when it happens, right? And like, just for a second, and one important point that we need to make about the crypto schemes is when we talk about zero knowledge, right, as a crypto scheme for private programmability, we really need to be aware that there is a limitation. And I know that maybe not everybody likes to hear that in this conference about zero knowledge, but right, zero knowledge inherently is about verifying some computation, right? That's where it comes from. It's verifiable computation. So you put in kind of a program that is converted into a circuit, right? And you verify the inputs that give you the outputs based on the execution of the program. But the execution is not done inside of zero knowledge. Compared to other potential schemes, such as FHE or MPC, that actually allow you to input different inputs and actually compute the output, quote unquote, live, right? Like the execution is done live. And that's important in how we think about specific applications when we build these protocols, these programmable protocols. So let's look for a second at the consensus level protocol. And we'll reference to the previous slide as well. There is these like simple applications sort of thing, and we call them simple for a lack of a better word. They're not simple to implement. We don't want to mislead anybody. Definitely not simple, Zcash. And this is kind of where really what we want to define as simple is like when there is really like, it's an application where you need only individual private state, right? So it's an individual that is interacting with the blockchain in some sense, right, with the protocol. And where there can be like sequential updates, right? Like, so if I make a transfer and Ying Tong makes another transfer, it doesn't matter kind of the order, they're commutative, but they can come one after the other because the state will be updated properly. And if one is sort of canceled or rolled back, the other one doesn't necessarily need to be affected. And the other one is this idea of commutative updates, yeah, correctly. And this is where like, Zcash or voting or identity comes in, where you really like can send something and send a proof, right? Compute something locally, kind of off-chain, and generate a proof that is going to go on-chain, right? That's sort of, for all of you familiar with privacy protocols, applications, this is kind of where we're at. And on the other hand, and this is where it really comes interesting, is that there are interactive applications, right? Like we're going to talk, Ying Tong is going to talk a bit about limit order auctions in a second, which we use as a kind of fundamental basis for these type of applications, where there's shared private state across actors, right? Like you cannot do a trade without actually having several actors combine these inputs in some way in the public state, right, on the chain. If you don't want them to disclose between them the trades, et cetera, when you have liquidity pools, all this stuff, in order to be private, you need to do it in a way that it's like async. And at the same time, you need to make it so that it's like an atomic state update. Because if you send a trade based on certain information and the other side of the trade is canceled, but you still sent your money and you cannot retrieve it, that's a problem. That's not going to work, right? And as we said, this is kind of like limit order auctions and multilateral trade credit setup, and that's definitely an interesting application that Ying Tong is also going to talk about. And really, like, I'm sorry if this bursts a bubble for some, but for these interesting applications or more advanced applications, ZKP is just not enough, right? Inherently, because what we said, it does not do a computation, it does verification. And when you're talking about blockchain, the computation needs to happen on chain, right? So I'm happy that most of you are nodding. And if you're not nodding and you don't understand, you can come to us or ask a question. Actually, is there any question around this? Does anybody want to refute this? Okay. Okay. So I'm going to let Ying Tong.
Yeah, so let's make this concrete by going through two motivating applications that capture the dynamic that we're interested in. So the first is MTCS. This is basically a system for finding internal debt cycles within a graph of liquidity and offsetting them without the need to seek outside sources of liquidity. So for example, if you're a merchant and you owe your supplier some money, and at the same time you're owed money by your distributor, then you could end up in a situation where you're illiquid but not insolvent. So you have to wait, basically, for your distributor to pay you before you can then pay your supplier. Now, if it so happens that your supplier owes your distributor some money, then the three of you form a debt cycle, and you can internally offset your debt without needing to take out a loan and pay interest on that loan. So now this is clearly an example of when the offset needs to be atomic. And furthermore, for multiple reasons, you don't want your connections in the graph to be made public. Another example that motivated us is the limit order auction, and this is far simpler than MTCS. So limit order auctions, we also want them to be private, and the reason is that when you trade in public on a DEX, you'll be front-run by a bot. And that's why all the big players trade on centralized exchanges where they have the privilege to be front-run by the exchange. And so we want private limit orders, and we absolutely want our limit orders to be executed atomically. So there's two variants of limit order auctions that are interesting. The first is the order book. So let me put on my glasses. So basically you have a make site and a take site, and both of them specify the desired input and output assets and amounts. So effectively, they specify the price at which they want to trade for this pair. And then there's a matching algorithm that takes place that forms two balanced, that fills both orders and forms a balanced transaction. Another variation of this is the very popular constant function market maker. Now, the only way that this differs is that you're not allowed to specify your price. So you're not allowed to specify your output amount. And in fact, the price here is determined algorithmically publicly. And after the trade, you shift the bonding curve on the liquidity pool. So something to note here is that by looking at the changes in the liquidity pool, we can easily reverse engineer the details of the order. And so in a naive constant function market maker, there is really no way to make a confidential order. And the best we can do is an anonymous order. Now, the thing about these two variants is that they are actually kind of the same thing. So if you consider a concentrated liquidity position, that's basically, if you make the liquidity position narrow enough, that's pretty much a limit order. And going the other direction, if you compose enough limit orders, you can approximate an arbitrary bonding curve. So these are equivalent. These two variants are equivalent. However, the decision to make the price discovery public in the protocol makes for a very different design decisions, as we'll see presently. Next.
Doesn't work? It's not working, the click? There you go.
Zero.
Oh, it's mine. Yeah. Okay. Sorry about that. So this was kind of like a very good example, and we actually took this example in our paper as kind of the basis for analyzing the different protocols that Tong is also going to talk in a second. And what we really tried to do is to have at least like a small kind of framework that would be really helpful in thinking about these programmability protocols. And really like limit order auctions were important because it's kind of like, feels like the minimal application where you actually need this interaction and aggregation, and you can build other applications based on this specific application. So in our paper, we actually present this three-phase computation model. The first phase, we call it the independent computation. This is what we said before, is like the single party inputs, there is some pre-processing, and there is no real interaction across between parties, right? We actually worked through kind of like an ideal functionality presentation, so I encourage you to look at it. And this is where we can use zero-knowledge proofs, for example, and we can use even some people are using like something like hardware attestations, etc. But we encourage the cryptographic security. And then, can you? There you go. And then in the middle, we have what we call a mediated computation, right? And the mediated computation is exactly this, is where like there's multi-party private inputs, and the computation is actually executed. So this is the limit order auctions, et cetera, where we aggregate data, right? And again, here is where we need the more sort of FHE or MPC, et cetera. There is also work done with hardware, and there's actually also work done with third parties, right? And we're going to talk in a second about these. And then the third one is this idea of a global computation, right? Because at the end of the day, all of this happens, and then in the global computation is where like the verification of all the execution and or independent computation and the mediated computation actually takes place, and where the state is actually updated, right? In a way, this is very similar or in line. We also got inspired by ANOMA's intent-based architecture, right? Like, because this is really where it comes from. When you have some protocol that or application that requires a mediated computation, the independent computation includes that intent, right? When you're doing a limit order, you're gonna, in the independent computation, probably generate a zero-knowledge proof that your intention, right, is valid according to certain rules and commitments and ownership rules and so on. And then in the mediated computation, it's going to take effect as a computation and then as an execution. And then in the global computation, you're going to see the update of the whole chain updated. And again, we have the specific ideal functionality. And just kind of briefly to go through these, as we said earlier, there's kind of these general purpose applications and specialized functionality. These are the protocols, most of the protocols that we looked at, but we didn't go into into detail with all of them, because as you can see, there's plenty of them today and they keep evolving. In the paper, we tried to actually do a bit of a generalization and categorization, but please, I encourage you to look at that. That's on the top part of this table, and on the left we have the different types of kind of privacy, right? So when we say extra protocol, we actually mean that there is kind of like that, like a protocol that is off-chain or through a mediator, through a third party, right? That is taking place. In that case, in most situations, the mediator or third party actually sees some of the data, right? The basic data that they need to actually aggregate, right? This doesn't mean that these protocols cannot have a more cryptographic version of these type of mediation, but today the default is that, right? This extra protocol. There's of course the hardware security, because you could have just instead of a mediator, like plug in a TE and sort of let that TE do the aggregation in an attested way. And then you have what we call a chaos event security, which is really like bring the cryptography in, right? at the end of the day, we call it K of n because even if you use something like homomorphic encryption, you're going to end up having to, decrypt the output, and hence you need someone to decrypt it. You don't want just one person, you want to divide that across parties. And this is kind of the categorization we had here. So we're going to go through some examples. I don't know if we have time to go through all of them. So
how much time do I have?
We have like 5 minutes.
Yeah, the approach we took in this SoK is instead of trying to exhaustively enumerate all existing protocols, we picked one representative protocol from each significant category, and we wrote UC-style definitions for each of them. So the first two protocols here, they implement an order book DEX, and the second two implement CFMM. So the first example we might hear a little bit in the later talk is ZSA swap. This is asset swaps on Zcash. And this is an example of a protocol that delegates privacy to some extra protocol solver. So here in the independent computation phase, the maker and the taker individually spend their input. They declare their desired output to some off-chain solver. So here the solver simply has plaintext access to all orders, does the extra protocol matching, and produces balanced transactions that are sent to Zcash, like a normal transaction. Now, a different implementation of the order book DEX is Renegade Phi. So it's pretty much the same shape, except that Renegade Phi's protocol defines a 2PC matching algorithm, whereby relayers collect transactions and then match them, try to match them with each other. So over here, if the match succeeds, then a balanced transaction is produced. And if the match fails, then no information is revealed. And in case of a successful match, a collaborative snark proving the correctness of the MPC is also submitted on-chain. So now we move into the implementations of CFMMs. The first one we're going to look at is secret swap, which is on secret network. So every node in the secret network runs a TEE with a consensus seed. So to execute a trade, the user encrypts it to this consensus seed. And inside the TEE, this is decrypted and executed against a public liquidity position. And then the output of the trade is then encrypted to the user. And of course, the price change on the liquidity pool is public. So Penumbra implements the CFMM in using a different primitive. In Penumbra, a user once again encrypts their order, but this time they encrypt it to a threshold of validators. And they encrypt it using a homomorphic encryption such that the validators can sum up the ciphertext of the orders and then decrypt the aggregate. So the aggregate is then executed as a batch in plaintext. The thing to note about both of these CFMM implementations is that they are only as anonymous as the size of the batch. So, for example, in secret network, if your transaction is the only one in the block, which is not hypothetical, secret network blocks really have only one transaction each, then just by observing the price liquidity pool change, I can reverse engineer your order. And the same holds for Penumbra. Yeah, so these are the, whoops.
That was, yeah.
Oh my God.
Are you hitting the right one? Don't hit. Yeah. There.
So yeah, those were the protocols that we looked at in detail in our SoK. And really, the whole process of comparing private limit order auction implementations has led us to identify the main trade-off. And it's not a surprising one, it's security versus expressivity. So for protocols like Penumbra and Renegade Phi that bring the mediated computation in protocol, they make it the responsibility of all consensus nodes. And the computation that's done by all consensus nodes is operating in a resource-constrained environment. And that's why we want to keep it as simple as possible. So in Penumbra, it's literally just adding things. Whereas in Renegade Phi, it's a way more involved computation. It's a whole matching algorithm. Whereas those protocols such as ZSA swap that move the privacy guarantees outside of the protocol can have more freedom to perform expensive computations. But basically the privacy guarantees fall on application designers. And furthermore, this potentially fragments the state or liquidity across different applications. So really, the choice between in-protocol versus extra-protocol should be informed by your application's requirements. Yeah.
Thank you. So just to finish up here, we wanted to lay out a couple of questions and ideas for the kind of future research and future work. So one thing that we really want is to have kind of like a UC proof of security for these privacy properties. We actually defined ideal functionality for several of these, but we didn't implement or like actually go ahead and compute the proofs, right? Like do them by hand. So we definitely encourage that. We want to continue exploring the question of the metrics and what are the categorizations that we do here, what are other hidden trade-offs potentially, how can we do this a little bit better in terms of efficiency for fixed programs, or how much work does it take for the consensus node, the security, right? Like security is different than privacy in some cases, but how do you manage both at the same time for robustness, right? And really what we are kind of what we hope we started with this work is to lay out kind of like a best practices framework in a way, in that so that whenever someone builds a protocol or those that exist can kind of be mapped to this, and there's easier comparison across protocols as well, right? And then of course think about every component of the technological stack there. And finally, if I can do a, can you help me here? No.
Yeah.
Oh, there you go, sorry. Yeah, so for this, just very quickly, we kind of dreamed about this idea for a second of building kind of this optimal programmable privacy protocol that really fits these three requirements, right? Like the three-phase computation model, and enables kind of the applications, enables expressiveness for user-defined programs while ensuring security of the application, right? Because sometimes when you leave very low-level programming to the user in the context of cryptography, you know, the protocol may be not necessarily secure. Like, I would definitely encourage anyone to ask Dara how difficult it is to ensure even a single functionality protocol that is private, how much it takes to ensure its security. And we also want the cryptographic level privacy, right? Ideally. I mean, of course, if you have an external protocol, then you're potentially doing some compromises, but again, that depends on the applications. And really, like, this potential direction that we outline includes kind of different cryptographic schemes for different computation phases, like the zero knowledge. We want zero knowledge for individual computation, and we want something like MPC or FHE for the mediated computation in order to be able to aggregate. And then we want to build potentially like a combined DSL. What we mean by that is that it can speak both engines, the language of both engines, right? The cryptographic engines. And so you can then easily, like you create kind of a separation where whenever you're doing independent inputs, right, you need to define the actors, etc. whenever you're doing independent inputs, it knows how to map that into its corresponding ZK circuit as a compiler, and whenever you're talking multiple inputs and aggregation, it knows how to talk the FHE language, right? And I think we think that one of the interesting things to do in this language is also to define kind of the privacy invariance. Like that way, whenever you're actually implementing these protocol or this application through this new DSL, you're going to potentially prevent unintentional leakage, right? I think some of this is being done at the level of other compilers. And finally, I think one of the ways that we could do this is to create kind of define or implement higher level primitives, like we were saying before. Instead of giving, I don't know, hash functions, commitments, and maybe Merkle trees, we can give asset transfer as a single application that is already ensured by more experts, because most of the time, these developers don't necessarily have the skills to make it secure. And hopefully by that, increasing security. And that's it. Thank you for listening, and sorry for the glitches and technical challenges. Good job.
Questions? Questions? All right.
This is more of an observation than a question. So